This next video is going to talk about eigenvectors and eigenvalues. For a certain class of square matrices A, there exist certain vectors x such that when the matrix is multiplied by them, the resultant vector is equal to the vector x times a constant, and we'll label that constant as lambda. So basically, we have a matrix A, and there exists a vector x such that when the matrix is multiplied by them, the resultant vector is this x times a constant we'll call lambda. And x is called the eigenvector, and this constant lambda is called the eigenvalue. Okay. The vector x is the eigenvector of matrix A, and lambda is the eigenvalue corresponding to that eigenvector. In German, eigen means same or self. It is thus a self vector, or one that gives itself back, multiplied by a constant, when the target matrix A is multiplied by it. So let's use this matrix A that we've used previously. It's a 3 by 3 matrix with the values going across 4, 6, 2, 6, 16, 3, and 2, 3, 9. We can multiply this A times a vector x sub 1. So 4, 6, 2, 6, 16, 3, 2, 3, 9. And we'll give x1 a vector, the property that we just described. When A is post-multiplied by x sub 1, the resultant vector is going to be equal to the x sub 1 vector multiplied by a constant. So one number that we can get is 0.374, 0.872, and 0.316. So this will be our x1, and when you multiply that, you actually get 7.360, 17.144, and 6.205. Which, you break that down, let me zoom out here. Okay, this will actually turn out to be this x1 again, 374.872.316 multiplied by a constant, and that constant is actually 19.662. So this equals, I'll write it here, x sub 1 times this constant that we'll label lambda sub 1. So this indicates that x sub 1 is the eigenvector of A, and lambda sub 1 is the associated eigenvalue. Actually, the matrix A has additional eigenvectors and eigenvalues, since the rank of the matrix is what? Yeah, the rank of the matrix is 3. And since the rank of the matrix is 3, there are 3 non-zero eigenvalues with associated eigenvectors that we'll demonstrate in just a second. But first, let's go over to Excel here. As you can see, I have our A entered in, and I've entered in x sub 1. Now when we do matrix multiplication, Control Shift Return, we find out what we found out over here. Okay? And I'm showing here that we do x sub 1 again, which we have here. Sorry, this is a little difficult to see. That's an 8. Is multiplied by a constant to get x sub 1 times lambda sub 1, which will be equal to a times x sub 1. Well, a little known secret that I didn't tell you before is that you can actually do division of matrices quite easily in Excel. At least I'll demonstrate with these simple vectors. So lambda is gonna be a constant, and we can take that by making it equal to this a times x sub 1 matrix divided by the x sub 1 matrix. Control Shift Return, and we do get 19.679, which is close to what we have over here, which is in your text. So it can be demonstrated once again that this is equal to matrix multiplication of our x here and lambda. And it does in fact equal what we got here. Of course there's rounding error or whatnot, but it's pretty close. So we can see what we demonstrated over here. Our matrix A times this vector x is equal to the vector x times a constant. And as I just mentioned, since the rank of the matrix A is 3, there are 3 non-zero eigenvalues with associated eigenvectors. So what that is saying, we go over here, we have A times x sub 1, and that's going to equal x sub 1 times this constant lambda sub 1. We can also have our matrix A times x sub 2, and that will be x sub 2 times a constant, as well as x sub 3 and lambda sub 3. So we have 3 eigenvalues with associated eigenvectors. So the second eigenvector is its associated, the second eigenvector and its associated eigenvalues is this one here. Our matrix A times a vector x sub 2, and that will be equal to that vector x sub 2 times a constant. And I'm going to demonstrate that on Excel. So our x sub 2, our second eigenvector, is equal to our matrix A, or it's equal to this, and then we're going to multiply them, A times this vector and it turns out to be this here, negative 0.2 and then negative 2.617 and then 7.444, which is close to the values that you have in your text. So dragging this out here, I have the same x sub 2, the same eigenvector here, and we're going to get our constant lambda sub 2. And as I showed in Excel, you can simply do this by taking this one that we calculated here and dividing it by the eigenvector, and we get 8, which is pretty much rounded. What we had in the text was 7.895. And then lastly here, we can do some more matrix multiplication, or more multiplication here. We're going to take our eigenvector, multiply it by the constant, and we should get the same thing as we have here, which is pretty much the same thing. Obviously it's rounded a little bit differently. So let's do that for the third eigenvector and eigenvalue. Do the same thing. A times this third eigenvector. And we get 1.338, negative 0.52, and negative 0.147. So to get this, we're going to take the matrix we just calculated, or the vector, divide it by our eigenvector. It's a simple way to get lambda sub 3 here, which we get to be 1.443. And lastly, let's multiply those together. Our eigenvector times our eigenvalue, and we should wind up with the same thing here. So what I just demonstrated is something that I mentioned when we started the video, that for a certain class of square matrices A, there exists certain vectors x such that when the matrix is multiplied by them, the resultant vector is equal to the vector x times a constant, which I said up here. And we can see that since this is the rank of 3, we're going to get 3 of those, where x is the eigenvectors, and these lambdas are the eigenvalues. So the vector x is an eigenvector of matrix A, and lambda is the eigenvalue corresponding to that eigenvector. It is thus a self-vector, or one that gives itself back, times a constant. So what we just did can be expressed in matrix form with all 3 eigenvectors combined and their associated eigenvectors in diagonal matrix form. And I will demonstrate this solely on Excel. Okay, so we can take, if you see here I have matrix A, and we can multiply that by matrix X, which that matrix X will just be a combination of all the eigenvectors. So here's A, and we're going to put X in here. So what I'm going to do is just copy and paste these eigenvectors in. So we can do matrix multiplication and multiply these two together. A and then X, Control Shift Enter. And you'll notice what we get is just what we get up here. So the first column is this one, so A times the corresponding eigenvector, and then A times the corresponding eigenvector for the second column and third column. If we come down here, you can see that this matrix A, the original matrix, times this matrix of eigenvectors will equal the matrix of eigenvectors times a matrix of constants, which is essentially what we just showed previously, except this is all combined. So I'm going to copy and paste this matrix X of eigenvectors. And it's going to equal, when we multiply it by another matrix, it's going to equal what we have here. So it's going to be these lambdas on a diagonal. So it's going to be in a diagonal matrix, leaving everything on the off diagonals to be 0. So once again, this is going to be equal to this one divided by our first eigenvector, and so on. Essentially what I'm doing is just copying and pasting these lambdas. So we see here that on the diagonals we have the constants. So once again, what we've demonstrated is that for the square matrix A, there exist certain vectors x such that when the matrix is multiplied by them, the resultant vector, or in this case matrix, which we have here, is also going to be equal to this matrix of eigenvectors times a constant, which we have the constants here. And there you go. That's about eigenvectors and eigenvalues for you. It's going to come in handy in the future, so I hope you learn this. If you have any questions, ask. Have a nice day.